of first law of thermodynamics. Okay, so we had seen the statement of first law of thermodynamics last time. Wherein we understood that in any thermodynamic process for an ideal gas, the net heat supplied is equal to the change in internal energy plus the work done by the gas. We saw that this heat is a path dependent quantity. Okay, whereas delta U, which is the change in internal energy, this is a state function, okay, or path independent. And we saw that W, which is the work done by the gas, this is also a path dependent quantity or a path function. We saw that in general, delta U is defined as this particular quantity, okay, where F is degrees of freedom, N is number of moles, and delta T is change in temperature in kelvins. So this formula had come from kinetic theory of gases. Okay. Then we saw that work done by the gas is integration of PdV, or area under the PV curve for the process. Okay, and therefore Q comes from the sum of these two. So this is what we had discussed in the previous lecture and seen a couple of examples of application of the same. Okay. Now today we will look at the specific application of these for the 4 standard processes. Okay. 4 named or standard processes. So let's begin with the understanding of that. Okay, so much of this you're familiar from chemistry, but in chemistry, remember that you write W on the left hand side of the equation because you write W as the work done on the gas, which definition becomes minus integration PdV. Here it is the work done by the gas, which definition is integration PdV. Okay, so just to understand here that work done by the gas is positive for an expansion process, where the volume is expanding, and W will be negative for a compression. And also to understand here that U is the total kinetic energy of the gas molecules. And that's how we got the formula for change in internal energy from the application of law of equipartition of energy and all that from kinetic theory of gases. Okay, so now continuing ahead, we will look at the applications of first law to standard type of processes. So our first example of a standard type of process will be an isochoric process. Okay. So as you know, this is a process where the volume of the gas is constant.
Sir,
Okay. So which means that change in volume is zero and pressure is proportional to temperature because volume is constant. Okay. So for an isochoric process, first of all, the PV graph, it looks like a vertical line because the volume is constant.
सर ऊपर का नोट नहीं करना था.
So in the last lecture, you taught us about the isobaric process, right?
Yes, yes. So today we will look at it in detail.
Okay, sir.
So an isochoric process like this, for example, you can see that A to B is an isochoric heating process, whereas B to A is isochoric cooling.
Sir, this was done.
Yeah, I'm just going for a recap of that. Okay. So
Okay,
for the
sir.
isochoric process, you have Q is equal to delta U because W becomes zero. W becomes zero because integration PdV is zero because your volume is constant, right? So Q is equal to delta U is equal to NCV delta T. So from this we get the formula that CV is F by 2R. And of course, you know that F is, and it is equal to 5 for diatomic gases. So this is the first of the standard processes. As you have mentioned, we have already discussed about this in the last lecture. But there's nothing more to it actually. Just understand this much only. So for example, how would you actually implement an isochoric process? You would implement it like this. You would keep your gas in a container of fixed volume. And then accordingly, you can either supply heat to increase its pressure and temperature, or you can withdraw heat. So container of fixed volume. Okay. And you have a heat element. So you can either supply heat, that is a process like A to B, which I've shown there, or you can withdraw heat from the gas. That would be a process like B to A. The pressure and temperature would be decreased in that case. Okay. Now let's move on to the next of the standard processes. So that you don't need to write down because you've seen this in the last lecture. Now the next thing, isobaric process. So as the name suggests, baric has to do with pressure or bar. Okay. So this is a process at constant pressure. So pressure is constant or dP is zero, change in pressure is zero, and volume becomes proportional to temperature because PV is equal to nRT. Okay. So on the PV graph, this type of process now looks like a horizontal straight line. So you can see that, for example, if I'm going from A to B, the volume is expanding. This would be an isobaric expansion. The volume at B is greater than volume at A. So temperature at B is also greater than temperature at A. Now coming to the specific of isobaric process, delta U of course is defined as NF by 2R delta T. Okay, this is a state function. So same for all processes, so independent of path. But the other things are path dependent, work done and Q. So work done, which is integration of PdV, because the pressure is constant, it just becomes P into integration of dV. So it becomes P delta V. Okay. And P delta V is also equal to NR delta T, because PV is equal to nRT and pressure is constant. So the work done is given by this relation, P delta V or NR delta T. And geometrically, you can understand the work done is this area. This area, which is whatever this pressure is, into VB minus V. This is the work done, which is positive for isobaric expansion, whereas it would be negative for compression. So that's the second of the three things. Okay, so delta U of course is a universal formula, as I told you. So it doesn't change from process to process. It's the same for all. Okay. Whereas this is of course a path function, W. So now we can see that Q, which is equal to delta U plus W, becomes NF by 2R delta T plus NR delta T. Okay. Or we can write this as F by 2 plus 1 into P delta U, because NR delta T is P into delta V, as we've seen before. So now Q here is also defined as NCP delta T, where Cp is called the isobaric molar specific heat capacity, or it is the heat capacity at constant pressure. Okay. So just make a note up to here, then we'll complete the discussion for this, because I think last time we had stopped at isochoric process, right? So isobaric, we need to write down everything.
Yes.
Yes, sir. Sir,
Yes.
sir, the barometers question comes in heat and thermodynamics only, na?
Can you speak a little bit louder, beta? Which
Sir, the
expression?
barometer one.
Just a second. Yeah, say again, which expression?
Sir, not in this. I'm asking about barometer.
What meter?
Sir, questions
Barometer.
related to barometers.
Barometer. Okay, barometer we'll discuss better. Okay. Barometry actually has to do with a subject called fluid mechanics. Okay, we'll discuss in that. I'll explain how the barometer is used here also.
Okay, sir.
So barometry is based on the principle of hydrostatic pressure, na? Density into G into height. Na? Pressure at a depth inside a fluid is given by rho gh. Na? Density into G into height. You know that concept, right?
Yes, sir.
So barometry works on that principle. So I'll explain how it works in those kinetic theory of gases type of questions. Okay, so now when you put together these two things,
Excuse me, sir. One more
Yeah.
minute, please.
yeah, okay. So when you put together these two things, you can see that this becomes so you get the formula for Cp. So this becomes something very important over here, that Cp is F by 2 plus 1 into R. Just like above, we had written that Cv was F by 2 into R. Okay, so we have Cp is equal to 7 by 2 R for diatomic gases, and Cp is equal to 5 by 2 R for monoatomic gases.
Done, sir.
Right. So one final thing here, that Cp is equal to Cv plus R. This F by 2 plus 1 into R, we can also write it as Cv plus R. So these two are universal facts for all ideal gases. Okay, so let's do a quick example problem involving these type of processes. So a sample of hydrogen at initial pressure of 0.5 atmospheres, volume of 2 liters, and temperature of 200 Kelvin is first expanded isobarically to a volume of 4 liters. And then cooled isochorically to a temperature of 200 kelvins. So we have to first plot the PV graph for the above two processes and find P2, P2, P3 and B3. Okay. Second, find Q, delta U and W for the isobaric expansion and again for the isochoric cooling. So these are extremely simple but standard type of questions at JEE level, especially JEE Mains level. So you have to just be able to apply the correct formulae by visualizing the correct processes. Okay. So if you remember the process by the PV graph or by simple facts of how we apply the ideal gas equation for the given definition of the process and all that, it's quite easy to work this out. Just try out this question, people. Yes, Vashish, that is correct. You will have to convert the quantities to SI units. Okay. So you should also know that 1 atmosphere is 1.01 into 10 raised power 5 pascals. Okay. And 1 liter is 10 raised by 3 meter cube. So 10 raised by minus 3. So the PV graph for this process will look something like this. First, we have the isobaric expansion. So let's say that's like this. And then we have the isochoric cooling. Let's say that's like this. Okay. So this is the starting point A, where the pressure is P1, the volume is B1. Temperature is T1. Okay. Now we can see that V1 upon T1 is equal to V2 upon T2. Isobaric process. AB, let's say. Okay. So means the pressure at the second point is equal to the thing. Okay. P1 is given to us as 2 liters and V2 is given to us as 4 liters. So T1 being 200 Kelvin, T2 will become 400 Kelvin. And then B to C, what is happening is that pressure is proportional to temperature. Okay. So from here it is going to a temperature of 200 Kelvin. So if temperature is becoming half, that means pressure will also become half. So 0.25 atmosphere. The volume remains constant. Okay, so these are all the quantities here. Okay, now let's calculate and verify all your answers for.
Sir, 1 minute.
Okay. So this was the first part. You have found out all these unknown quantities. Okay, so more people have sent the answers. Tantresh, Yash, etc. I'll just verify and give you the final answers. So for the first process, what is happening? It's an isobaric expansion. So W we can write as, or even better as P delta V. So that is going to be the pressure of 0.5 atmospheres into the volume expanding from 2 to 4 liters. Okay. Or P1 into V2 minus V1, that thing. Okay. So this becomes 0.5 into 2 liter atmosphere. So that is 1 into this much in joules. Okay. So I think it will become 101 joules with a positive sign. That is the work done during the process AB. Delta U is of course NF by 2R delta T. So here it's hydrogen gas. So we'll take F as 5. So 5 by 2 into NR delta T, or 5 by 2 into P1 into V2 minus V1, because okay, so we have this. So you can write this as 5 by 2 into the same thing, 0.5 into 4 minus 2 liter atmosphere. So 2.5 into 101 joules. So that's our delta U for the process AB. And QAB, just use this. So okay. Similarly, for the second part,
Excuse me, sir.
yeah,
Screen is not visible.
yeah, I'm coming back. Just give me a minute. Just give me a moment, guys. The whiteboard software is hanged for some reason. I just have to reboot that software.
Yes, no, sure.
Yeah, so this is for the isobaric process. Now let's come to the isochoric process. BC. Okay. So there W will be 0 because it's isochoric. Q is equal to delta U equal to NCV delta T. So that is N into 5 by 2R into T3 minus T2. So now to make this convenient, we can also write this as 5 by 2 into this thing, T3 minus T2, because NRT3 and NRT2 P3 is equal to P2 because it's, oh sorry, V3 is equal to V2. It's a isochoric process. Okay, so basically NR delta T can be written as V delta P for isochoric process. Okay. So this will simply become 5 by 2 into, that was 4 liters. Now the pressure was decreasing, so this will be a negative quantity. So 0.25 was the final pressure in atmospheres and 0.5 was the initial pressure. 5 by 2 into 4 into minus 0.25 in liter atmosphere. So that will become minus of this and this cancel, so 2.5 liter atmosphere. So that's basically minus of 252.5 joules. That is the value of QBC as well as delta U for the process BC. So you have to have this kind of clarity and where to apply what formula, and also how to use the equation of state PV equal to nRT all the time. Okay, so remember that in any expression, if we are using NR delta T, so that is NR T2 minus T1, it will always be written as P2 V2 minus P1 V1 because PV is equal to nRT is being used.
Sir,
Yes.
sir, can we consider 1 atmosphere is equals to 1 into 10 raised to 5 Pascal? It's okay for approximation.
Generally, see what happens that the question will give you the approximation that you can approximate just like in mechanics, questions give you the approximation that you can take G as 10 meters per second square. So like that, here the question will ask you to approximate it as 10 raised power 5. If the question doesn't ask, then you should take a more exact value, which is 1.01 into 10 raised power 5. Okay.
Okay, sir, understood.
Okay. Now, next thing we'll look at is isothermal process. And as an application of isothermal process, we will look at a question involving a barometric type of setup. So I'll help you understand how to apply the principle of barometer also. Okay. Now, before we come to this, now we'll also discuss about the experimental setup of an isobaric process. Okay, so suppose we want to expand of a gas at a constant pressure P, where P is greater than atmospheric pressure, for example. Okay, so one way we could achieve this quite easily at an experimental level is that we could have this kind of a setup. So these are what we call non-conducting or adiabatic walls of a container. Okay, and there is also a free piston. So free means the piston can move easily up or down, which is massless. Okay. And that's also adiabatic or non-conducting. Okay. We have a sample of ideal gas inside, but we have a heating element. So you can always supply heat to the gas. Okay. Now this is loaded with some mass, let's say. Okay. And the piston has area equal to E. So what will happen is at any point of time, if you look at the piston's free body diagram, the force acting on it is P into A because of the internal pressure of the gas. Okay, and P naught into A because of atmospheric pressure, and of course the weight of whatever is placed on it, mg. So if the piston is in equilibrium, the pressure of the gas has to be equal to P naught plus mg by E, because forces have to balance. So now if heat is supplied very slowly through the heating element, okay, while the mass on the piston is kept constant, what will happen is that P equal to P naught plus mg by A remains constant, while the volume of the gas expands. So work done is positive by the gas, and its temperature also increases. So internal energy also increases in such a way that it's undergoing an isobaric expansion. Okay, because the pressure is constant. So this laboratory process would achieve what is called a quasi-static or very, very slow isobaric process, where at each point in between, as the gas is going from an initial state to a final state, so you're supplying heat very slowly, and as a result, this piston is moving up very slowly. So moving up very slowly means it's always almost in equilibrium. So that is the meaning of the term quasi-static. Almost static, or always almost in equilibrium. So through that, we will achieve that isobaric process, where the gas will undergo the change exactly as predicted by the PV graph or the application of first law of thermodynamics to isobaric process.
Done, sir.
Okay, so this is an example of, as I said, what we call a quasi-static and reversible isobaric expansion. See, quasi-static means extremely slow. So the system is almost at equilibrium at all points on its path or PV curve. Okay, similarly, next up, we will look at the third of the four standard processes, which is the isothermal process by name.
Sir, can you scroll one?
Yeah, I'll go back just a bit. Okay. So isothermal process is one where temperature is constant. So change in temperature is zero. Okay. So pressure is inversely proportional to volume. So we can see that isotherms are rectangular hyperbolic curves on the PV space. Okay. For example, A to B. So pressure is inversely proportional to volume. So this is an example of an isothermal expansion. So at any point in between, the pressure is like this. So PAVA is equal to PVVV is equal to P into V. And the temperature is uniform throughout. So also this means that if the temperature is uniform, it means that the change in internal energy is zero, because delta U is, and here delta T will be zero. So this is something important for isothermal process. So Q is equal to W, which is integration of PdV. Okay. Now further integration of PdV becomes nRT by V from whatever initial state to final state. So temperature being constant, it is a logarithmic integration, as you know. So Q is equal to W is equal to nRT natural log of V final upon V initial for isothermal process. So Q equal to W will be positive if V final is greater than V initial. So ln of V final upon V initial will be a positive quantity. Okay, so that's for an expansion. Whereas Q equal to W will be a negative quantity if V final is less than V initial, because that would involve a compression. So this is all the information about isothermal process. So I'll just minimize a little so you can also write down the portion above for quasi-static process. Okay, so hope the concept of isothermal process is. Achha, you want me to wait just a moment? Finish writing that page. Okay, now let's understand a question with relation to barometry. Okay. So the functioning of a barometer, let's understand that first. So barometer is typically a device used to measure atmospheric pressure, as I'm sure you must be aware. It uses an open container and an inverted thin glass tube. So what is done is there is mercury which has a density of 13.6 gram per cc. Okay. And this part is vacuum. This part is 1 meter. And if the reading of this is some X, then the atmospheric pressure comes out to be density of mercury into G into X. So at sea level and STP, X comes out to be 76 centimeters. So atmospheric pressure comes out to be 13.6 into 10 raised by 3 kilogram per meter cube into 9.8 meters per second square into 0.76 meters. And this is the value of standard atmospheric pressure that we know. Okay. So how this experiment is performed is actually first that glass tube, this one, this is the glass tube. So the glass tube is first filled with mercury right to the top. So the glass tube is filled with mercury. Okay. Then we place some kind of a seal. Okay, like this. Okay. And then it is inverted and placed inside the mercury container. So this is the mercury container. So we invert this, right? So this closed end is on top. Okay. It's full of mercury. And this side is sealed, so mercury cannot come out initially. Okay. And we place it such that the portion above is exactly 1 meter or 100 centimeters. And then what happens is now the seal is removed. So when the seal is removed due to excess pressure, mercury comes out, leaving behind a vacuum gap on top. Okay. So mercury flows out of the tube leaving a vacuum gap at the top till pressure is balanced. Okay. And that happens when X is equal to 76 centimeters at STP. And from that we are able to measure. Okay. So just make a rough note of this part, then I'll explain exactly how that pressure balancing situation occurs. So this is the process of the setup of the barometer when it is used to measure atmospheric pressure. Okay, Prince, this is clear so far. What we are doing in the experiment, that's clear, no?
Yes, sir.
Okay. I'll explain exactly why that rho gx becomes equal to atmospheric pressure when the mercury reaches equilibrium. Okay. That comes from the principle of hydrostatics. Yes, you are asking something?
Sir, there is also something regarding 84 centimeter, na, the true reading.
84 centimeters will not be for mercury, or it will be at high pressure. Okay, 76 centimeters is the standard atmospheric pressure at sea level. If you do this calculation, 13.6 gram per cc into 9.8 meters per second square into 76 centimeters, you'll get that exact figure of 1.01.
Got it, sir.
Okay, so the working principle of the barometer, that is something like this.
Sir, 1 minute.
We are not.
Yes, sir. Done, sir.
Okay, done.
1 minute.
Done, sir.
Okay. So the working principle of this has to do with the fact that hydrostatic pressure is rho gh. That is, inside a liquid, when we go to a depth of h, the pressure increases by rho gh. Okay. That's why I told you we'll be studying about this in detail in a chapter called fluid mechanics. But anyhow, you know the basics of hydrostatic pressure from before. So we can use that over here. Okay. So if we have a container having fluid of density rho, then if we select any 2 points such that one is deeper by a depth of h, okay, then we know that the pressure at the lower point will be equal to the pressure at the higher point plus rho gh. Right. This is the concept of hydrostatic pressure. So this concept is familiar to all of you, right? In 9th standard, you must have studied. Okay. So this is what is utilized in the working principle of the barometer. So what happens is when we take the beaker of mercury, okay, and into that we invert the tube like this, okay, with the seal in place, and in the beaker the mercury is, let's say, up to this level, and in the tube mercury is completely filled up, and this is 1 meter. So now if we compare, we can see that this point's pressure, let's say this point is A, and this point is on the surface, so this point is B. The pressure at the point A right now is how much? It is density of mercury into G into 1 meter. Whereas the pressure at the point B is equal to 1 atmosphere or P naught. Okay. So we can see that PA is greater than PB. So that is why when the seal is removed, okay, mercury flows out, because fluid always flows from higher to lower pressure. Okay, so this fluid flows out like this when I remove the seal. And finally, what happens is that as the fluid flows out, it leaves a vacuum gap at top. So the height of the mercury column is becoming less. Now, where the vacuum gap is there, the pressure is 0 because there's no air. Okay, so now if mercury has come down to this level where this has become some X, okay, this whole thing is still 1 meter, but it doesn't matter. Okay, the mercury level is only up to X. So it has left behind a vacuum gap. So the pressure there is 0. Okay, so now at this point A, how much the pressure is? At the point A, the pressure is equal to 0 plus density into G into X. And at the point B, the pressure is atmospheric pressure. Okay, so if there is equilibrium of the mercury, that means it should not flow. So pressure at A should become equal to pressure at B. So atmospheric pressure should become equal to rho Gx. This is the working formula of a standard barometer. Of course, the barometer has to be built with a certain amount of care that air bubbles should not find their way into that gap where vacuum should be there. So usually this mercury in the beaker, it is covered with some sealant on top. Okay. So, but the basic working principle is like this. Okay. That's how we get this formula, that the atmospheric pressure is equal to density of mercury into G into whatever this level of mercury is in the open tube, okay, inverted open tube. So hope this working principle is clear now. Prince and Diti, both of you understood this?
Yes, sir.
Yes.
Oh. Now see, in thermodynamics, we won't be using a typical barometer for doing questions, okay, but you can have variations of the barometer. Okay, so for example, one very simple variation could be just to do with equation of state of an ideal gas. Okay, so for that,
Sir, true reading and false reading also, no?
because of there might be a false reading because there is some gas which has atmospheric air or any gas which has leaked into the container or into the tube, right? So now suppose what is happening is that in our barometer, we observe that the mercury level has fallen up to this. because there is some gas present over here. There are gas at pressure P1, let's say. Okay. Now this level has, let us say, become 55 centimeters. And this is mercury only. And we know that atmospheric pressure is equal to, let's say, an approximate value is given, 75 centimeters of mercury. So when atmospheric pressure is given in terms of mercury height, this is called the barometric reading for atmospheric pressure. So it means that the atmospheric pressure is actually equal to density of mercury into G into whatever that height is. Okay, and we have to convert this in SI unit to get it in pascals. So you might wonder that how pressure is given in terms of centimeters, because it is equivalent to the pressure due to a 75 centimeter column of mercury. That is what it means. This statement, when we say that the pressure is so many centimeters of mercury, it means that barometrically it's equal to so many centimeters. That means it's equivalent to density of mercury into G into whatever number of centimeters. Okay, so that is what is given to us in the question. Okay. So now what we have to do is, knowing that this is 1 meter, okay, and the atmospheric temperature is equal to 27 degrees C. First of all, we have to find the pressure of the gas inside. And secondly, if the cross-sectional area of the tube is, let's say, 5 centimeters square, then find the number of moles of gas inside the tube. Yes, okay. So this type of question involves the barometric principle, where you have to now understand that the principle still holds that at equilibrium, the pressure at this point should be equal to the pressure at this point. So equilibrium condition is that pressure at A is equal to pressure at B. Now pressure at A now will become P1 plus density of mercury into G into X. Why it will become P1? Because there's no vacuum here now. So there is gas at, okay, so this is the gas pressure above the mercury column in the barometer. That was supposed to be vacuum, but some gas has got stored over there. So because of that, okay. And pressure at the point B is nothing but atmospheric pressure. Point B is at an open surface. So that's why its pressure is equal to atmospheric pressure. Now we will substitute from here that P1 will become P0 minus rho Gx. Now we will substitute this. Okay. So P0 is density of mercury into G into 75 centimeters. We can just substitute like this one. And this is, sorry, X. And X's value is given to us as 55 centimeters. So we can see that P1 is equal to density of mercury into G into 20 centimeters. Okay, now. And once we know this, we can just use ratio and proportion, and we can see that P1 upon P0 is 20 by 75. Okay. So P1 is equal to 4/15 of atmospheric pressure, or P1 is equal to 4/15 of pascals. Okay. Or you can do a more exact calculation, and P1 is So density of mercury so you can do this calculation and check out how much it is. That's the first thing, and rest is very simple. You have to just use equation of state, PV is equal to nRT. But in this, that you have to just use the trick that since you know that it is a glass tube, so the tube's walls are conducting. Okay, so for the second part, you have to just use the trick that glass tube. Okay, so glass is heat conducting. That means the temperature of the gas inside will be equal to the atmospheric temperature outside of 300 Kelvin. And then use P1 V1 is equal to N1 R P1. So from that you will find the number of moles. Okay, so P1 is that much.
Nice.
V1 is going to be L minus X into area of cross section. So that is 45 centimeters into 5 centimeters square. Okay. And R is 8.314 joules per mole Kelvin. So from that you will find the number of moles. Okay. So I'm not completing the calculation here, but just telling you that this is how barometric approach is used in solving a question related to an ideal gas. And how you have to interpret the data given in terms of barometric pressure.
Sir, the upper part was remaining.
Sorry, come again, Prince.
The upper part was also remaining to write.
Achha, you have to write down the upper part. But you understood now how the calculation is done now?
Yes, sir.
Okay, good.
Sir, sir, sir,
Yes, yes, Prince.
sir, can you scroll down?
Yeah, finish with this, no?
Yes, sir.
Okay, so hope this question was clear.
So,
Now we come to the last of the standard processes, adiabatic process. So this, as you know from chemistry, I'm sure, is defined as a process where the heat exchange is zero. So there is no heat exchange. So the physical representation of this process would be just like we had for the isobaric process. You have a piston, but this time we can add or subtract mass from the piston to make the gas expand or contract. But the difference is there is no heating element, and the walls of the container as well as the piston itself are adiabatic or non-conducting in nature. So we have some kind of a gas side. And these are non-conducting or adiabatic walls. And this is a free piston, which is also adiabatic. And we have mass m on it. So if mass is slowly added on the piston, then the gas undergoes an adiabatic compression, wherein delta U plus W is zero. So W will be negative because work is done on the gas, okay, by the mass on the piston. Okay. So work done by the gas is negative. Okay. And delta U will be positive. That is what happens in an adiabatic compression. Whereas if mass is slowly removed from the piston, the gas expands adiabatically. So W will be positive, work done by the gas, and delta U will be negative.
Done, sir.
Yes.
Yes, sir.
Okay. So formula wise, you
Sir,
can
1 minute.
see, yeah. Formula wise, you can see things are very easy for adiabatic process. So for any adiabatic process, whether it is an expansion or a compression, Q is equal to 0 and W is equal to minus of delta U. So it is minus of NF by 2R into delta T, because obviously delta U has the universal formula, which is a state function. But here work done, which is the path function, becomes this, because delta U is the state function. So regardless of whatever process, delta U has this formula. Okay, but the complicated thing about adiabatic process is the relationship between pressure and volume. So that we will derive by applying this definition of adiabatic process, that Q is 0, by applying it on first law of thermodynamics and also using the equation of state PV equal to nRT. So as you know, from that we will get the relationship that PV to the power gamma is constant, where gamma is what we call the adiabatic constant. It is the ratio of Cp is to Cv.
Yes.
So let us look at the pressure volume relationship.
Sir, can we continue this in next lecture?
Yeah, just it will take a couple of minutes, don't worry. Because then you can work out questions based on all these processes now. You don't have to leave out anything. So it's quite easy actually, there's nothing difficult about it. Okay. So Q is 0, that means delta U plus W is 0. So that means for a small change, we can say du plus dw is 0. So n Cv dt plus P dV is equal to 0. This is our first equation here. Cv is of course F by 2R. Okay. And is equal to nRT. That means P dV plus VdP is equal to nRT. That becomes our second equation. So this is ideal gas equation in differential form. So we've used the product rule over here to differentiate, because P, V, and T are all variables here. Nothing is constant. Of course, number of moles is constant, but so what we do is now substitute nR dt equal to P dV plus VdP from equation 2 to equation 1. So we have N, or we have, you write this as Cv by R into P dV plus VdP. Plus P dV is equal to 0. So we have Cv by R plus 1 into P dV plus Cv by R into VdP is equal to 0. And from here on, it's a very obvious kind of process further. So Cp so now this quantity Cp by Cv is called gamma, the adiabatic constant. So we have gamma times dV by V is equal to minus of dP by P, and if we integrate this now from, let's say, P1 V1 to P2 V2, we get the relation that minus ln P2 by P1 is equal to gamma ln P2 by P1. And next step, once we use the principle of indices here, we'll get the relation that P1 V1 to the power gamma is equal to P2 V2 to the power gamma, or in general, PV to the power gamma is constant for an adiabatic process.
Done, sir.
Okay.
Sir,
Sorry?
just a minute. I have not yet completed writing this.
Yeah.
Sir, can we leave now?
Yeah. Just write down this final thing over here that we get now P2 by P1 to the power minus 1 will become V2 by V1 to the power gamma. Okay. So that gives us the final relation that P1 V1 to the power gamma is equal to P2 V2 to the power gamma.
Excuse me, sir. Can you please scroll a bit up? A bit.
Scroll up. You haven't written that portion. Okay. Just a moment.
Yes.
So PV to the power gamma is constant. Okay. So this becomes the relationship between pressure and volume for an adiabatic process. Okay.
Sir, I didn't understood how you derived equation number 2. So can you explain that part again?
Yeah, I'll explain. So equation number 2 has come by differentiating PV equal to nRT. Okay.
Okay, sir. So we
PV is equal to nRT को differentiate कर दो दोनों तरफ. So change in PV is equal to a change in nRT. Okay. Now here P and V are both variables. So first into differentiation of second plus second into differentiation of first. Okay. And here NR is constant. So this. Got it now?
sir. Thank you, sir.
Okay. Okay. Right. So with this, we complete today's session.
Sir, just a minute. I'm just copying it.
Bye, sir. Thank you, sir.
Bye, sir. Thank you, sir.
Okay, people. So you can finish writing this down. But with this, we finish today's lecture. Next time, we will look at applications of all these in numerical problems. So start working out questions from H.C. Verma chapter of first law of thermodynamics and the next chapter after that, which is called the molar specific heat capacities of gases. So the questions of applications of first law, they are divided into 2 chapters in HCB. So you can solve questions from both of them. There aren't too many questions. So you can start solving everything now.
Okay, sir. Bye, sir. Thank you.
Bye, sir. Thank you.
Okay, people. That's it then. Bye.
Done, sir. Bye, sir.